Welcome back. In our last video, we considered poles and singularities, and we gave quite a few examples to back that up. Now, in this video, we would look at the concept of residues, the formulas necessary to calculate residues, as well as the statement of what we refer to as the Cauchy Residue Theorem. The Cauchy Residue Theorem would be absolutely vital for us when it comes to the evaluation of integrals in complex analysis. Now, let us start first and foremost with the residues. As always, make sure to like, share, and subscribe, and turn on your notifications so you do not miss any of our videos. Let's begin. First off, we will talk about the residue at a simple pole. This is a pole of order 1. This is the basic possible pole that we evaluate at. Now, in this case, the formula for the residue would simply be, if you are evaluating the residue of the function at z0, then we'll simply take the limit as z tends to z0, z minus z0 f of z. And the result of this would simply be the residue at that simple pole. This is very, very interesting to keep in mind. Simple poles are the easiest and are very commonplace when it comes to a lot of functions. So knowing their residue is very, very simple and easy to find. The next kind of residue calculation that we can make is residue at a pole of order n. Right? Let's take z0 still. So this time around, z0 is a pole of order n, order 2, order 3, order 4, and so on. Now, in this case, we would write a very robust formula to help us calculate the residue of f of z at z0. Now, how would we state this? We state it as 1 divided by n minus 1 factorial, limit as z tends to z0, the n minus 1 differential of z minus z0 raised to the power of n f of z. There we go. So this formula is the generalized formula for finding the residue of a pole of order n. 1 over n minus 1 factorial, limit as z tends to z0, the n minus 1 differential of z minus z0 f of z. Z minus z0 raised to the power n f of z. So you will notice that when n is equal to 1, this will be 1 divided by 0 factorial, that is 1. And then the 1 minus 1 differential is just going to be the default, the basic, the original differential. That's d raised to the power 0, this is 0. That's just the basic function. And then z minus z0 raised to the power of 1, f of z, that reduces back to the simple pole. So knowing the generalized formula is indeed a very, very important concept. And then one very important formula we must avoid not to skip is the residue that occurs at an essential singularity. Now, for an essential singularity, the residue of the function, in this case, at that point, would simply be the limit as z tends to infinity of minus z f of z, right? So usually we say at z tends to infinity. So the residue at an essential singularity, this is what we have. So limit as z tends to infinity minus z f of z. So these are very, very important values or valuations of the residue that we need to know. Now, we would take a very simplified example based off the fact that it is an example of a question that we can easily solve. We will take an example of a residue at a simple pole, and then we will devote yet another video to discuss or to find the residue at other kinds of poles. Now, this would also help us weigh in on the relationship that exists between the residue and the Laurent series. Remember, we said that the first term of the principal part of the Laurent series also refers to the residue at that pole. But that is already a very known fact. Now, how can we show that that is true? Now, this is what we are going to do. We are going to take an example. We are going to find the residue of this using the Laurent series, and then we are also going to find it using the formula and see if we obtain the same result. So we have e raised to the power z divided by z raised to the power 4. That's the value. So we are finding the residue of e raised to the power z divided by z raised to the power 4. This is the function. We are looking for the residue of this function. Of course, from here we can easily see that if we set the denominator to 0, we can easily see that z equal to 0 is the pole of order 4, right? We have z equal to 0 as a pole of order 4 in this case. Now, if this is the truth, the very first thing is, let us write out the Laurent series for this function. Now, how exactly are we going to generate that? Very simple. Based off this, remember the Taylor series of the topmost region is going to be, of course, you have 1 over z raised to the power 4, then you have 1 plus z squared over 2 factorial plus z cubed over 3 factorial plus z raised to the power 4 over 4 factorial, and it goes on. Now, if we were to expand this bracket, we are going to have ourselves 1 divided by z raised to the power 4 plus 1 divided by z raised to the power 3 plus 1 divided by 2 factorial z raised to the power 2 plus 1 divided by 3 factorial z plus 1 over 4 factorial, and it continues. Now, what do we notice? We notice that whatever happens to the right of this will be the analytic part, and whatever happens from here to here is the principal part. The principal part has 4 terms. Now, by the Laurent series, remember, since we have already identified the principal part and we have identified the analytic part, we would see that from this enclosure, and I'll write it clearly, we have 1 over z raised to the power 4 plus 1 over z cubed plus 1 over 2z squared, then plus 1 over 6, 1 over z, which is this term, and then you have 1 over 4 factorial, right? And then you have 1, and then you have z over 5 factorial, and it goes on. Now, this is the first term of the principal part. And what is the coefficient of the first term of the principal part? 1 over 6. So it means that the residue of f of z, in this case, as z equal to 0, is indeed 1 over 6. That is the residue, because it's the coefficient of the first term of the principal part. It's the coefficient of the first term of the principal part. This is how we utilize the Laurent series in finding the residue of the function. Now, we can also find this residue using the normal formula. Remember, it's a pole of order 4, so we would need the full form of the formula. I'm going to write it out. We have 1 divided by n minus 1 factorial. In fact, we might not even need to write it out because we already have it here. So you can just apply this. It will be 1 divided by 4 minus 1 factorial d raised to the power 4 minus 1 divided by dz4 minus 1. Then what would we have inside? Of course, we are taking the limit, let's not forget, as z tends to 0. And then inside here we have z raised to the power 4 e raised to the power z divided by z raised to the power 4. That is the evaluation of this formula. So we have here 1 over 3 factorial, that's going to be 6, limit as z tends to 0, the third differential of e raised to the power z, because z raised to the power 4 and z raised to the power 4 would have cancelled out. That's the plan. Now, the third differential of e raised to the power z will still remain e raised to the power z, because the differential of e raised to the power z will never change. So your limit as e tends to 0, as z tends to 0 of e raised to the power of z. And when we evaluate this, this will be e raised to the power 0. So it means that the residue of f of z would simply be 1 over 6. So what have we noticed? We see that from the Laurent series, we got 1 over 6. From the formula, we also got 1 over 6. So that tells us instantly that we can find the residue of a function at a particular pole using the Laurent series generated by that value, by that function. Now, of course, there are going to be a bit of discrepancies as regards to how exactly it works or when best it works. Now, this is working very, very well at break or pain points, which of course we have identified. But having the residue formulas makes it easy for us to go straight to a formula and plug in the poles into the formula in order to quickly identify or solve what the result would simply be. So those are very, very important key points. Now that we have noted this, we will then draw the curtain on this series or on this video by stating the Cauchy Residue Theorem. Now, it's important to state it because, as I said, it will form the basics of, or the basis of our foray into the evaluation of integrals. Now, let's state this as rigorously as we can. And there we go. The Cauchy residue theorem tells us that let f of z be analytic within and on the closed contour C, except at the poles z equal to z1, z2, z3. Now, those poles could be simple poles, multiple poles as the case is, or multiple ordered poles as the case is, interior to the contour. Then the integral of the function is going to be equal to 2 pi I times the sum of residue at those poles, which means in order to get the value of the integral, of the evaluation of the integral, the very first thing you need to do is find the residue at those poles. Once they fall into the contour, which is very, very important in this case because the contour will talk about the permissible region. Once they fall into the contour, you will sum the residue of the poles that fall into the contour and then multiply by that by 2 pi I. That will give you the value of the integral of that function. So this is a very, very important theorem that guides our evaluation into integrals. Now, before we go into evaluation of integrals, as I said earlier, we will take a couple of more examples on residue so that we would be able to understand clearly how it works, as well as different ways in which questions can be solved or put forward in order to find the residue of different functions. As always, make sure to like, share, and subscribe, and turn on your notifications so you do not miss any of our videos.